Welcome to SK Pass International College. We are going to continue with our lesson on hybridization. If you have not subscribed to this channel yet, I'm pleading with you to subscribe to the channel, like the video, and comment. In case you have any question, you can bring your question on board. Okay, we are going to continue with our hybridization. In our previous lesson, we have the definition, the various types of hybridization. If you have not watched that video, I urge you to kindly watch that video before you watch this one. In today's video, we are going to talk about the next type of hybridization. So with the next type of hybridization, we've already treated the sp hybridization. So the next one will be sp2 hybridization. Under the sp, we said that it is formed as a result of the mixing of s orbital with the p orbital. So two hybrid orbitals are formed, and then the angle, the bond angle under the sp hybridization is 180 degrees, and then the shape of the sp hybridization, or the shape, is what we call, it has a linear shape. So any molecule having sp hybridization has a linear shape. A typical example is the beryllium chloride we gave example. So let's look at the second type of hybridization, which is sp hybridization. sp2 hybridization. So with the sp2 hybridization, this is also a type of hybridization formed as a result of mixing of an s orbital. So this is an s orbital with two p orbitals. Already we stated that we have the p orbital itself is degenerate. So there are three divisions, subdivisions. We have the px, py, and pz. So here we are going to mix two of them. So px plus py. So it can be like this: px, py. So this is an s orbital plus other two p orbitals. So you realize that we are missing one s orbital with two p orbitals. So in this case, we are supposed to form three hybrid orbitals. So here, this hybrid orbital will also be like this. So you can see they are having three hybrid orbitals formed. So under sp2 hybridization, the question is, they can ask you how many hybrid orbitals are formed after hybridization undergoes sp2. The answer is it forms three hybrid orbitals. So with these three hybrid orbitals, one thing we need to know is that they can ask you the shape. If you look at this shape is in the form of a triangle. If you can see this, the geometry wall, this is a triangle. So looking at this geometry, this has formed a triangle. So we can say the shape of this is trigonal, is a planar. A trigonal planar. So that is the shape of sp2 hybridization. And then the angle formed from here to here is 120 degrees. So it has a bond angle of 120 degrees. The shape of this is a trigonal planar. And we can say that three hybrid orbitals are formed under sp2 hybridization. Okay, let's give a typical example. Let's give a typical example using BF3. So with this example, we can pick the central atom. And I've told you that when we say central atom, we are referring to the most electropositive element. So the element which is most positive, electropositive, is what we are considering. So here boron becomes the central atom. Boron has atomic number 5. So if you want to write the configuration, it's going to be 1s2, 2s2, and then 2p1. So this is 5. So this is what we call the ground state electronic configuration. The ground state electronic configuration. So let's look at writing this in the excited state. Now, why would this undergo an excitation? Why would there be the need to promote electron? The reason is, if you look at boron being the central atom, it is bonded with 3 atoms of fluorine. And in chemical bonding, we say we don't deal with the core electron. So we only deal with the valence electron. So the valence electron for this is 3, which is 2s2, 2p1. Because these have the same quantum numbers, you cannot just say this. So it's 2, this 2s and 2p. They form the valence electron. So we have 3 of them. So in actual sense, if you are mixing only these 2, you will be left with 1 fluorine. Therefore, there is the need to promote an electron from this lower energy to the other energy level, so that they can also have, this can also be bonded. The other fluorine here can be bonded to the central atom. That is why there is the need to promote an electron. So if you are doing that, it implies that we have 1s, this is an s orbital. Okay, so let me draw the detailed form. These are 2. And when you pick the p orbital, it is degenerate. So this is what we are saying for the ground state electronic configuration. We are having 2s2 and then 2p1. But we need to promote an electron from this state. We need to promote an electron here. We need to promote an electron here to this orbital. And as soon as there is a promotion of electron from a lower energy to a higher energy, that's what we call an excitation. So we promote an electron from a lower energy to a higher energy. So the excited state configuration will be like this. So we have promoted an electron. You realize that now we have 2x1, then 2px1, and then 2py1. So with this, you can see clearly that there have been 3 more electrons, 3 extra electrons. So quickly look at this. If you want to draw that, this is our boron as the central atom. So these are the 3 1x, 2x, and then 2ps, 2py. So this is how we form. And this boron, being the central atom, is bonded to this fluorine. So we should know the shape of fluorine. Fluorine here is an F orbital. So fluorine will also be down barely shaped like this. Another down barrel shape like this. So there will be 1 electron here. This will donate 1. This will also bring 1. So there are 2 here now. There's 1 electron here. This will also bring 1 electron. So there is a bond there. Covalent bond is formed there. This will bring 1 electron. This will also bring another electron. So another covalent bond is formed. So in actual sense, this is what we have formed. This is what we have formed. This is fluorine. This is fluorine. This is fluorine. So this is BF3, and this is how it is formed. And the bond existing between this is sp2 hybridization, or the type of hybridization, sp2 hybridization. Then the bond angle from here to here is 120 degree, and then the shape of this is what we call a trigonal planar. So that is for sp2 hybridization. With this, if you want to look at the next type of hybridization, which is sp3. With sp3 hybridization, in this type of hybridization, it is formed as a result of mixing an s orbital with 3 p orbitals. So look at this. I have an s orbital, spherical in shape, plus p orbital, 3x plus py plus pz. So you can see, if you are asked how many hybrid orbitals will be formed after sp3 hybridization, or anytime we have sp3 hybridization, how many new hybrid orbitals are formed? There are 4 new hybrid orbitals formed. So we form something like this. So this is tetrahedra. Tetra means 4. So the shape of this sp3 hybridization, any molecule which is having sp3 hybridization, that molecule is tetrahedral in shape. And the number of hybrid orbitals formed is 4. 1, 2, 3, 4. But we miss an s orbital with 3 p orbitals. So that is sp3 hybridization. In this example, the best example we can give for this type of hybridization is methane. The best example is methane, CH4. In this case, you need to consider the central atom, which is carbon. 1s2, 2s2, 2p2, because carbon is having atomic number 6. So having said this, I've told you already that we don't use the valence electron, and the core electrons, we only use the valence electron. So we are going to concentrate on this. So this is a ground state electronic configuration, but there are 4 of the other atoms. So we need to what? Excite, or we need to promote electrons to the other group. So look at this. Carbon in the excited state, this is not part. So this was having what? 2 of the electrons. 2 of this. And this is also having 1, 1. This is the ground state, but you need to excite an electron. You need to promote this electron from this state to this side. So this will be written as now we have only 1 left, and then when we extend the other ones, they are all having 1, 1 electrons. So this is what we are talking about. It's now having 4 hybrid orbitals. So this is our carbon. This carbon is now having 4 hybrid orbitals. So the first one will be here. Another one is here. Another one is here. Another one is here. So this is my carbon. It's tetravalent in shape. Now this carbon is bonded to hydrogen. Hydrogen is also spherical in shape. So we can break this. This is hydrogen, another hydrogen, another hydrogen, another hydrogen. So these are the hydrogens. The hydrogens will bring 1 electron each. And then the main one will also pair up. Will pair up like this. So in actual sense, we have managed to form methane. Okay, it is having 4 covalent bonds like this. And the bond that exists, the angle between this is 109.5 degrees, and it's a single bond. And then the shape of this is tetrahedral. So thank you for watching this video. Subscribe to the channel and then comment. Thank you. See you.